continuing with the tangent graph, I did want to make note of one more thing. When we were doing secant and cosecant graphs, we had asymptotes as well. And we had an asymptote equation that represented every asymptote because, again, they're infinite. So for the asymptotes for tangent, notice that they're occurring every pi radians, like I said. So pi times n if n is an integer. And then we can just pick one of the asymptotes. So typically it just makes more sense to pick pi over 2 because that's the first one to the right of 0 where that occurs. But again, I wouldn't be wrong if I said 3 pi over 2 or negative pi over 2, but just to be consistent with each other, this is our original asymptote equation. So if we have transformations, horizontal transformations, we can apply them to this asymptote equation. Okay, let's go ahead and try that with this. I'm going to actually attempt the asymptotes first, and you can just see how that works. Before I start, I want to make note of your period. So your original period is pi. So if we have a horizontal stretch of 2, like we do in this problem, then our pi is going to stretch by a multiple 2. So now your period is 2 pi. So if we apply that same horizontal transformation to our asymptotes, remember our asymptote are at pi times n, right, plus pi over 2. So if we're applying a stretch of 2 to those asymptotes, that's going to give us 2 pi n plus pi. So we have an asymptote occurring at pi and then every 2 pi radians to the left and right of that. And that's really helpful because that'll make it easier to graph. So if we come up with the asymptotes first, we know, hey, there's an asymptote at pi. So again, I'm going to set it up the same way I did before, just because it makes sense for my scale. And again, I want 2 periods here. So note that I did 3 periods originally in the first. We'll look at 2 periods here. So again, that asymptote is located at pi, and then it's going to occur every 2 pi radians. So my next asymptote actually would not occur until 3 pi. And the one before that would occur at negative pi, because again, we're counting every 2 pi radians. So what's nice about the tangent graph is it has that pattern again. There's no vertical stretch. So when I do my tangent graph, I know that it's rising from left to right. And my zeros are located directly in the middle of my asymptotes. And I'm going to actually make my 1s every 2 tick marks on my y-axis. So on this first quadrant point right here, I have a low of -1, but again, it's going to go lower. And then I have over here at my first tick mark over to the right, I have it at 1 as well. And then it's increasing from left to right. So again, here and here. So everything is equally spaced again, just like every other graph. Okay? So that is what that looks like for a tangent stretch. So we can apply any horizontal transformations to the asymptotes. I think it makes it easier to graph as well. But you can also just apply the points being stretched out that way too. Okay? So we're going to look at here, we're going to look at what a cotangent graph is. And what's really nice about the cotangent graph is that it's very similar to the tangent, but remember it's the reciprocal of tangent. So if you think about the reciprocal of 1, it's going to be 1, -1, it's going to be -1. But then you also have other values you have to consider, right? So you have 1.7 or √3. Your reciprocal of that is going to be 1 over √3, which is a smaller number. So the cotangent graph is actually going to be like a flipped version of the tangent graph. And we'll take a look at what that